Thank you, Lassi, for the introduction, and let me also put on the recording on this end. So, okay, so hello everyone. If you have any questions or comments during the talk or after the talk, feel free to interrupt me at any time. So you can just speak up, or you can raise your hand, or you can write in the chat. I'll see the chat on another screen if you have any messages there. Okay, so then let's get on with the actual topic. So before going on to this this mathematical talk, I want to give a little bit of a background just to give everyone a heads up of where we are going. So about the positions, as Lassi already mentioned. So so starting August this year, I'm an assistant professor here at Tampere on tenure track, and from the beginning of September, also an academy research fellow. And also from the beginning of September, I'm also a lecturer at University of Jyväskylä, but I'm currently on leave from Jyväskylä, so I'm working at Tampere. So at some point, in about a year's time, I will decide which university I want to stay at. So at the moment, both these options have a positive probability, and I can't predict yet how things will turn out, but just to be transparent here, these are the two courses available. Okay, and I'm part of this Finnish Center of Excellence in Inverse Modeling and Imaging, which is funded by the Academy of Finland. And we have 8 universities in it. And so we are now here in Tampere, and the other 7 are on the map there. Okay, so this Center of Excellence was previously in Tampere as well. I didn't bring it with me. It was with the Inverse Problems group in Hervanta. Okay, so then let's go on to the actual topic. So this is essentially my abstract. So I'll start with physics, and from physics through some modeling, I'll end up with a partial differential equation, which is not unusual. But then what I'll do with that PDE will be perhaps something a little more unusual for many applied people. I'll try to extract something geometric out of that PDE, and then within that geometric setup, I'll study and solve inverse problems. And then once I've done that, I'll translate those problems back into physics, or the conclusions back into physics to the extent possible. So that physics is not just a source for mathematics, but it is also the goal, so that I also want to give back to physics, physics to make these things applicable. So if you want to ask me whether I'm a pure mathematician or an applied mathematician, my go-to answer is that I am an applicable mathematician. Okay, so let's then see what this means in practice. So first, describe what modeling means to me in broad strokes, and then I'll go into the specific case of modeling geometrically these elastic things. And then finally, I'll discuss a couple of inverse problems related with that. So although this is in principle a math talk, there will be just a few theorems here and there. And if the theorems are not stated very precisely, if you want more precise statements, of course you can ask me, but I just want to give the main ideas and not focus on the technical detail. And most importantly, there will be 0 proofs. So if you want to discuss details, I'll be happy to do that. But I assume most of you will not be entertained by that as much as the bigger pictures. So let's start with this modeling thing. So well, the name of the Center of Excellence is Inverse Modeling and Imaging. And the goal that I have is in line with this name quite well. So I want to make sure that the mathematical results that I prove, because that is what I do eventually, I prove theorems, and I prove them about imaging and inverse problems. I want them to correspond well to physical models. And that is the kind of driving force. And I'll give 2 examples to make this goal concrete. Okay, so the first example is elastic geometry. And this is something that I will describe in much more detail in a bit, but I'll just start with a quick description. So anisotropy means that the wave speed depends on direction. So at the same point, depending on which way you are going, the waves go at different speeds. So that is anisotropy. And if this anisotropy is somehow weak of a very specific form, then these elastic waves, they will follow Riemannian geodesics. So there is a kind of a well-studied description of what happens to these waves, and it turns out to be in this realm of Riemannian geometry. But if you have general anisotropy, so you make no assumptions of the symmetry of the material, and there are heavily anisotropic materials within our own planet, even very deep inside it, then this Riemannian geometry is not enough, and you need to do Finsler geometry. Okay, so you need to geometrize it a little further, and then there is a theorem by myself and Martin de Hoop, Matti Lassas, and Teemu Saksala. So with some idealized travel time measurements from interior earthquakes, they will uniquely determine a Finsler metric arising from elasticity. So in this elastic model, it will be uniquely determined by the data, but not in a fully general Finsler setup. So what this means is that there is a certain balance here. So this model of elastic geometry, it's kind of narrow enough so that it's useful. So that if you go all the way to kind of include all of Finsler manifolds, then this theory becomes weak. We don't have a uniqueness result anymore. It fails because the model is kind of too broad. But if you only do Riemannian geometry, it's too narrow. So also we need enough generality to allow for all physical phenomena that we want to include in our model, and maybe even a little more to leave room for exploring something else, or something beyond the current model. So this is the balance. So it needs to be broad enough and narrow enough, and Riemannian geometry is too narrow, Finsler geometry is too broad, but somewhere in between is a balance, and that kind of balance is something that I'm quite fond of. Okay, for another example in a different direction, looking at cosmology, so on cosmological scales, most information is carried by electromagnetic or gravitational waves, and both of these travel at the speed of light. And if you do some kind of geometric measurements, which I will not give the detailed description here, but if you do these measurements geometrically, there is something you cannot see. So the fact that you're using only things that go at the speed of light will leave what is called a conformal gauge freedom. So there are some things that are inherently invisible. So if you want to fully determine the structure of the space-time, that is to find a Lorentzian metric, so we are essentially talking about general relativity here, then you need particles that satisfy these conditions. They need to be slow enough and fast enough. So slow enough means that they should not go at the speed of light, because that causes trouble, but they should be fast enough in the sense that they have a significant portion of the speed of light, because otherwise they will never make it all the way to us across cosmological distances. Well, they should also not be disturbed by electromagnetic fields near the detector, so near our planet, near our solar system. So it should be an electrically neutral particle. And for a good physical model, the particles should actually exist and be detectable. That is always a fun component of any model. Okay, so with this shopping list, there is exactly one type of particle that fits the deal, and that is the neutrino. There are several neutrinos. Different people will give different numbers, but the usual number is 3. And all of these neutrinos have essentially the same properties, and they will work here. Okay, so I'm currently studying geometric neutrino data with Günther Ullmann, and I won't go into much more detail here, but there should be a result within a year or so. And of course, I'll be happy to share a bit more details before that if anyone is interested. Okay, so these are 2 examples of geometric modeling related to physics. So the physical models are, I hope, getting pretty far from the simplest toy models, and also the math needed then it turns out to be quite elaborate. But that is what I try to do, to kind of tackle these hard inverse problems with geometric tools. Okay, so to give an idea of what geometrization means, and that is a word that I'm fond of and will be repeating a couple of times here. I want to describe a well-known example of gravitation to give a flavor of what it is. So let's start with Newton's theory of gravitation, which I hope is familiar to many. So here gravitation is a force, and force causes acceleration. So the gravitational force exerted by the sun causes the Earth's trajectory to curve. So the Earth does not go straight, but instead it curves in roughly a circle around the sun. So this force here is described by a simple formula. It's Newton's universal law of gravitation. And the equation of motion is an ODE. It's Newton's second law in the Euclidean space Rn, or rather R3. And this space R3 will stay fixed throughout the evolution of the system. So there is nothing funny going on in the geometry. And this Newtonian approach is very straightforward to use, and it's often a good model. So it's kind of simple to apply, you get good results. I have no complaints about that really. But then there are some things that it cannot reach, and for those things you need to go a little further. And now there is Einstein's theory of gravitation, which is of course known as general relativity. So here gravitation is not a force, it is an interaction between geometry and matter. Okay, so interaction between geometry and matter, and that even as a concept is a little more complicated. So now the sun causes the space-time to curve, and the Earth goes straight in this curved geometry. So there are no forces anywhere, just that the sun interacts with the space-time, causes it to curve, and the Earth goes straight. And a straight line in a curved space is called a geodesic. So there is a simple equation for the motion of the planet. It is the geodesic equation, and it's a nonlinear ODE, but it's a kind of a well-understood and well-behaved thing. But that is not the only equation of motion. There is also an equation of motion for the geometry itself. That is Einstein's field equation. And it is a nonlinear system of coupled PDEs. And it's a bit of a mess, but well, that's how nature seems to be, so that's what it is. So that's kind of the setup. And this model is, of course, much harder to use, but it can reach phenomena which are inaccessible to Newtonian gravity, or which Newtonian gravity predicts wrong. And what is important to me today, it provides a more geometric way to see the essential structures. I'm not really interested in anything phenomenologically new here today. I just want to give a geometric point of view and then benefit from that point of view. Okay, so with these Newtonian and Einsteinian gravitation models in mind, I want to ask whether there is a similar theory of elasticity. And that is something that we do have. The full details have not been worked out. It's in the process, but I want to describe now how this thing works and what are the main ideas and how the geometry looks. So before getting there, I need to talk about elastic waves, because the geometry will have to do with these waves. So it's a bit of an introduction to the physics of solids. So I'll start with something called the stiffness tensor. So if you have an elastic material, and if you displace it from equilibrium, it tends to return back. That's just basic elasticity. And the restoring force, which is known as stress, will depend in a linear fashion on the displacement relative to neighboring points, which is known as strain. And this linearity is just an assumption, but it is valid for small displacements, and I will be working only with small displacements so that my equations are linear. Okay, and notice here that the displacements and also the restoring forces are actually only relative. So imagine an elastic object like a rubber ball. So if I take the rubber ball and I move the entire ball in a different position, there will be no restoring force. Also, there is displacement, but there is no relative displacement. The different particles within the ball are still exactly the same distance apart from each other. But if I squeeze the ball, then the different particles in the ball will get closer or further away from each other than they used to be, and that will cause a proper physical restoring force. Okay, so that's just why everything has to be relative in an elastic material in this sense. And this linearity is known as Hooke's law. And when you have a linear relation, there is some kind of a spring constant, essentially. There is a coefficient of proportionality, and that is the stiffness tensor. I put the word tensor in quotes because it does not really behave fully as a tensor, but it is something close enough. So the stress and strain, they are both symmetric matrices. So if I have a linear map that maps a matrix into a matrix, it should have 4 indices. And that's why the stiffness tensor carries these 4 indices, I, j, k, l, and it will depend on the position x where we are looking at the thing. And this will fully describe the springiness of the material, the restoring forces no matter how you deform or twist your material. And this tensor has some properties. It is very symmetric, has these symmetries. It's not fully symmetric, but very symmetric. And it's also quite positive. Okay, so for all symmetric matrices, this kind of a property holds. So it's not important for us today what these exact properties are, but just that there are some properties. It's not just any collection of numbers in that 4 index thing. Okay, and quite often I'll end up eventually working with a density normalized version. So I'll define the stiffness tensor C with a density rho, and I'll denote that by lowercase a. Okay, so then I'll look at elastic waves. So now I have Newton's second law, which relates acceleration to force, and the force comes now from Hooke's law, and that gives me the elastic wave equation. So in this elastic wave equation, there are 2 terms. So in the second term, there is, well, density times acceleration, which is essentially mass times acceleration. And on the left, we have the force term. So U here, which kind of solves this equation, U is a displacement field. So at point x and at time t, the particles are displaced from equilibrium position by this vector U. It's a vector valued solution. So if you look at this thing, so here, so this is the displacement. I'm taking the derivative to get a relative displacement. I'm multiplying by the stiffness tensor to get a restoring force, and I'm differentiating again to get a relative force. So that's kind of a quick way to read this equation. Okay, so that is the elastic wave equation, which I'll abbreviate with U. Well, it's also a female she, but that will be unrelated. So if the material is anisotropic, so this the stiffness tensor C has no more symmetries than is necessary, then you cannot ignore the vector nature of this equation. So there are scalar wave equations, but they are only valid if the material has a lot of symmetries. Otherwise, you have to play with actual vector valued things. And elastic waves that arise from earthquakes or mass quakes or any kind of quakes you might want to study, they do satisfy this equation pretty well. So there is a hostile major event like an earthquake, and of course that is a very high amplitude, and I'm not really asking anything about the dynamics of that event. I'm only looking at the ripples, the waves coming out of that event further away, and those will have a very small amplitude, and they are well modeled by a fully linear model. Okay, and now there's something a little more technical, but just to maybe give some flavors and maybe new ideas. So supposing this stiffness tensor and the density are constant. Then in the case of constant parameters, it makes sense to try to write the plane wave solutions to the wave equation. Okay, and it turns out that if you plug this plane wave ansatz into the equation is satisfied if and only if this equation holds. So here, as in the sequel, I'll be implicitly summing over any repeated indices. So I'm summing over j, k, and l here in this equation. Okay, so you get a condition for these things. So here this vector capital A is the polarization vector. So it describes in which direction the particles are actually moving from the equilibrium. And that doesn't have to have anything to do with the direction of propagation of the wave. So those are two different things. Omega is the frequency, and this P is known as the slowness vector. So notice that usually if I write a plane wave, I would not take the frequency omega in front of the whole thing, but now I decided to do this, and that slightly changes the meaning of this P here, so it's not the momentum, but it is actually something called the slowness, which is essentially the inverse phase velocity. And what I had here in this equation, so I multiplying this vector A, there was an identity matrix, and before that another matrix. And that other matrix I will call the Christoffel matrix gamma. So it depends on position x, where we are evaluating things, and it depends on the slowness vector p, and is defined by this formula, again, summing over j and k. And because the stiffness tensor has its properties, this Christoffel matrix is symmetric and positive definite, so it has a wonderful spectral theory. We can talk about orthogonal eigenvectors and that kind of thing. Okay, so if you look at the elastic wave operator, it has kind of a principal behavior, so the high frequency main behavior, and that is captured by the so-called principal symbol. So talking about symbols is comes from a field called microlocal analysis, which studies these kinds of things. And what I just want to say here is there is a very explicit form for the symbol, and in a moment there will be a meaning for the symbol, what it implies. But the technical details you can ignore. I just wanted to mention that there is a machinery in this direction. Okay, so you can think of microlocal analysis essentially as studying plane waves at points. So you can somehow freeze things over and study plane waves at a point and then ask how things move. Okay, so as I mentioned, this vector A was polarization. And in isotropic cases, when you have a fully symmetric stiffness tensor, then the polarization vector has two options. It has to be parallel or normal to the slowness vector P, which is the direction of propagation. So if the parallel polarized wave, so where the oscillation and motion are in the same direction, which is known as the P wave or the pressure wave or the primary wave, that is always faster than the one where the oscillation is sideways with respect to the propagation. And those sideways waves are known as shear waves or S waves or secondary waves. So I'll be calling them just P and S. Okay, so in anisotropic elasticity, so when you lose your symmetries, it does not work quite as nicely anymore, unfortunately. So the fastest polarization is then called quasi-P, and the slower ones are called quasi-S. So just the way things are called, it doesn't have a deeper meaning. But now these polarization vectors of the Christoffel matrix, the polarization vectors are eigenvectors of the Christoffel matrix. So they are in fact orthogonal. So the condition we had on this polarization was essentially an eigenvalue equation, written maybe in a funny form, but it's still of that nature. Okay, so this decomposition of a wave into polarizations only really works at the level of singularities, unfortunately. So, well, if you have a constant and fully isotropic situation, then you can write your wave as a sum of a P wave and an S wave. But when things start to vary and get anisotropic, this kind of decomposition gets worse. Well, you can still do this, but then these individual polarizations will no longer satisfy any PDEs. Instead, they will satisfy some pseudo-differential equations. And that makes life harder, and I don't want to go there really. Okay, but I do want to study the singularities. So what I'm studying here, or what I want to use here, is the arrivals of wave fronts from an event. So I'm not looking at the full smooth solution to my wave equation. I'm only looking at the singular components. so the wave fronts. And the wave front is actually a technical term as well from macro-local analysis, but it is also a good physical description of what it actually means. So imagine just a very rough wave front where things are non-smooth, traveling through the material. So the singularities of the solutions of the elastic wave equation follow the Hamiltonian flow determined by the principal symbol. Now that is a mouthful, but that is the connection between the singularities and the principal symbol. So the principal symbol actually describes what happens to the singularities. And this bullet point here is a major theorem in micro-local analysis, and I assume it doesn't make much sense at first, maybe, and it doesn't have to, but just there is a way to describe what happens to singularities. And we can just use it as a black box. So we had a condition. So the slowness vector P and the polarization A and the singularity at X should satisfy this condition. Well, I only kind of argued this in the plane wave case and so on, but actually it turns out to be true in full generality. So this is the condition we have. And I don't really want to keep track of the polarization vector A, other than that I want it to be non-zero, which of course means that the determinant of that matrix has to vanish. So the admissible slowness vector P, where these singularities can exist, they form a set called the slowness surface. So if I fix a point X, all the possible P's where this condition is satisfied form the slowness surface. And I have a picture of it right here. So this is a three-dimensional thing, just given in slices. So on the left, this is just a two-dimensional slice through a three-dimensional picture. So the slowness surface comes in three branches. So there's the blue, red, and green branch. And the blue one is the innermost one, has the smallest slowness, so it is the fastest one. So that's why the name slowness. So it kind of behaves inversely. And it behaves much better than the outer one. So the quasi-P slowness surface, this blue one, behaves better than the quasi-shear ones, these red and green ones. And there's a couple of reasons. So first of all, the blue one is convex. So the red one is not exactly convex, it's a bit concave in a couple of places, and that is a major technical nuisance. And also, the red and green, these two shear wave things, they intersect each other. And so it seems that they always have to intersect each other somehow. So it kind of makes these things harder to analyze when the eigenvectors or the eigenvalues degenerate every once in a while, but not always. And also, there sometimes isn't even a global description, so you cannot always write things cleanly as a union of three surfaces. So if you try to follow these curves on the right, you'll notice that the red and green curves are actually just kind of a single two-sheeted surface around the origin. So the shear waves get a little messy geometrically, so I'll only be focusing on this innermost thing, this quasi-pressure wave. Okay, so now that we have something about these elastic waves, we can talk about this geometry. So what kind of geometry this leads to. And the basic concept is distance when we're doing geometry. So if you have a Riemannian manifold or any other kind of thing, the basic concept is distance. So if you know the distance between any 2 points, then you can compute areas and angles and curvatures and everything else. And this distance is actually also determined with a smooth structure most of the time. So all other things are kind of subordinate to distance. So if I want to have a geometry, I should describe what the distance is. So in elastic geometry, the object itself is the elastic body, like the Earth or a drum or whatever it is you want to study. and the distance is travel time. So I measure distance in units of time rather than space or length. So we declare the distance between 2 points x and y to be the shortest amount of time it takes for a wave to travel from x to y. And this kind of definition is somehow secretly clever, because as I mentioned, the shear waves are kind of ill-behaved. But if I'm only looking at the shortest amount of time, it means that I'm only looking at the fastest wave, and the fastest wave is this quasi-pressure wave. So with this definition, I'm kind of secretly dropping out everything shear from my system. Okay, so that is the geometry. So I could, of course, just declare this to be the geometry, but the unfortunate thing is that if you actually want to do anything in differential geometry, this is not a very concrete description. So you need to somehow describe something in somehow more technical terms and in somehow more tractable terms. And I'll do that in a minute. But this is a very kind of a heuristic picture that if you know the distance, then you do indeed uniquely know the full geometry, but it's somehow not easy to calculate from distance alone. Okay, so then I'll go into something called ray tracing, or what would be called ray tracing in geophysics. So we can think of these seismic or other elastic waves as point particles in different ways. And these point particles here are called phonons. So these elastic waves, they are related to this displacement field, this field U. And the particles corresponding to the this physical displacement field are called phonons. If you have another field, you have another particle. So the particles corresponding to the electromagnetic field are called photons, and so on. So all the particles in physics correspond to their own fields. And now that we have fields of elastic waves, we also have particles, which might not match your intuition of the word particle, but still that is a valid way to see things. And to see these as point particles, there are three ways. First one is just the physical principle of wave-particle duality, which says that the two descriptions should be essentially the same, and there should be features of both behavior visible. And that is indeed true, but it's very vague. So to make it more concrete, you can study wave packets, for example. So you can write a solution to your wave equation, which is very narrowly supported, and well, it usually spreads in time and all that. But especially if you take a suitable limit, so you shrink your packet, you get somehow a description of a point particle from your wave equation. Or you can use microlocal analysis, which gives you a nice tool set to study the singularities of solutions of equations as point particles. Okay, but these three things are the same, are one and the same to me. So these are just kind of different ways to see it, maybe different levels of technicality, different aspects, but it is the same underlying phenomenon. So that you can think of waves as particles. Okay, now once we have these particles, the question is, what do they do? So how do they travel? And now comparing back to the gravitational thing, so the traditional view is that the trajectory of the phonon is not straight, but it is curved because the wave speed varies. And the new view that I want to promote here is that the phonon goes straight in a curved geometry, so it goes along a geodesic, and the geometry is curved by variations in wave speed. So in the Newtonian picture, the planet would be curved because there is a force, but now in Einsteinian view, the planet actually goes straight, but the curvature of the space-time is where kind of the interaction is hidden. And it's the same thing here. So I want to hide the variations in wave speed into the geometric structure. And that is beneficial when it comes to solving actual physical problems, as it turns out. Okay, so this is how my phonons travel. They go straight in this weird geometry. And well, a concept from differential geometry is that a metric induces connection. What it means is that for every definition of distance, that is a natural definition of straightness. And that is, well, I mean, you can put it much more technically, but that is somehow the main point. For every concept of distance, you can define what it means to be straight. So in elastic geometry, we measure distance in travel time, and these waves, or at least the quasi-p-polarized waves, actually go straight in this geometry. And Fermat's principle says that these phonons, so these particles corresponding to these waves, they go straight in this geometry. So the Fermat's principle just becomes this. So the principle is about going straight in the relevant geometry. It is not about taking the shortest path. So this kind of straight formulation of the principle turns out to be a very robust way to see things, and it's valid in a lot of cases where the short thing doesn't really work out. And so the short thing will fall apart usually if you have somehow interfaces, or you have long distances, or you have shear waves. The description can fall apart immediately. But if you use this straight going business, then things work out just fine. You just have to be careful what it means to be straight, but then that will have a sensible definition. Okay, so I did mention that I'll be needing Finsler manifolds, and so I should tell you what they are. So I'll start with what is a Riemannian manifold. So, well, first of all, what is a manifold? So a manifold is somehow a smooth set, and you can think of it as a subset of a Euclidean space. So for example, the unit sphere S2 sitting inside the Euclidean space R3 is a perfectly valid example of a smooth manifold. And if you want to think of manifolds in general, you can just think of that example for the purposes of today's talk. And at every point on that manifold, there is a tangent space. So take any point on the sphere, there will be a tangent space to that sphere. And what Riemannian geometry is that you put an inner product on all of those tangent spaces. So Riemannian geometry is just a collection of inner products. And that surprisingly leads to a very rich and useful structure. And now, once you have an inner product on this vector space, then of course it induces a norm. So what a Finsler manifold is the same kind of thing. It's a smooth manifold, but it has a smooth and strictly convex norm on every tangent space. So every inner product will induce a norm, but not every norm will come from an inner product, which is familiar from functional analysis. And now the same thing can be now applied in these tangent spaces. So a Finsler manifold is a more general beast. Okay, and there are some axioms that it should satisfy in order to actually be Finsler manifold, but I will not go through them here, but I'll just describe what then follows. So once you have this concept of a norm on every tangent space, you can define, for example, the length of a curve. So the length of a curve would be the integral of the norms of the velocity vector. And now those individual norms you now know how to compute using the norm, which is called a Minkowski norm. And then, well, you get the definition of length of a curve, and then you can look for the shortest curves, and that will lead you to geodesics. Okay, and well, there is tangent space Txm, and has a dual space T star xm, the cotangent space. And when you have a norm, it also has a dual norm, and the dual norm will have the same properties. So I did not list the properties, but the same kind of smoothness and convexity and all that will be inherited to the dual side. And I will have to make a little pass through the dual world in a moment, so I had to mention these side of things as well. So, so now this is what elastic Finsler geometry then is, and now this is a mouthful, so I'll take a while to try and digest this with you. So the first sentence here packs the connection between physics and geometry. So the co-sphere of the elastic geometry is the slowness surface. Okay, so we defined the slowness surface earlier. It somehow comes from the physical description, starting with the stiffness tensor, and there was a Christoffel matrix, and you find a surface. So it is defined in terms of physical parameter. So, but what I want to do is to kind of define a a norm on every tangent space. I want to give a Finsler metric. So to give a norm on a space, well, I can just the same, I can give the dual norm on the dual space. I can describe it on that side. And to give that dual norm, I can actually just declare its unit sphere. And that is what is most natural to do here. So the co-sphere is the unit sphere on the dual space. And I declare that to be exactly the slowness surface. And that is what leads to elastic geometry. So declaring this unit sphere on the dual side to be exactly the slowness surface, this is kind of the link condensed into a single sentence. But of course, it is very condensed, so it takes a little while to sink in, at least to me. So now, this so-called elastic manifold corresponding to these pressure waves, it is now a Finsler manifold, and it has some additional properties, so it's not just Finsler, but it's something a little better. As I mentioned, there was this balance that a fully Finsler manifold is not exactly quite as good as the things that you get from elasticity. And to repeat, phonons go straight in this geometry. Okay, so this is the geometrical world that I've been living in for a while. And mostly for quasi-P waves, so if you look at shear waves, they are problematic, and I will not discuss them today. Okay, so that is the setup for the geometry, and then there's this list of inverse problems, which I'll just describe very, very quickly. Just to give a flavor of what the actual problems are. So I'll start with geometrizing the question. So the typical inverse problem would look like this. You are given some boundary data, and the task is to find the reduced stiffness tensor everywhere. Okay, well, a typical problem. Given some data, then try to see what this parameter is inside the planet. Okay, so a more geometric formulation. Given some data on the surface of the planet, find the co-sphere, that is the slowness surface at every point. Now, this is a very geometric way to see over it, kind of sounds much more geometrical, but it turns out to be the same question. But it is easier to answer. And you can take a little bit, take another step a little bit further. Well, okay, so from this slowness surface, one can then compute material parameters, so it is kind of the same question. And you can go a little further and get into something that is a practical question for a geometer. Given some boundary data, find the Finsler manifold, or perhaps find its co-sphere bundle, which is kind of a description of all of these co-spheres. Okay, so that is the kind of question that I'll be asking. So the theorems that I have will have to do with Finsler manifolds, and it has to do with finding indirectly an anisotropic stiffness tensor. So this is the link, and I'll just give the kind of results in a more mathematical form. So there is a problem that I've been working on with a student of mine, Keijo Mönkkönen, who is actually in the audience. So in 1905, Herklotz and others solved the inverse problem for a spherically symmetric planet. So if you assume a natural condition, then if you have an isotropic wave speed, which only depends on the radius, it will be uniquely determined by boundary distances, so travel times of earthquakes. And if you have a spherically symmetric non-trapping Riemannian manifold, so whatever that might mean, but anyway, some kind of a natural family of Riemannian metrics, then it is always of this good type of Herklotz. But if you have a Finsler manifold, that is, if you have a less symmetric physical model, then this is not true anymore. And we know that the materials within our planet are not fully isotropic, so this Finsler description is actually needed to get a good description of what goes on. So there is still a Herklotz condition, it looks different. And if you, well, this is a nonlinear problem, but you can linearize it and it will lead to something called X-ray tomography. So it is, well, sounds like a medical problem, but it turns out that the same math will be valid for looking at the patient's bones and looking at the interior of the planet Earth. Okay, so that was one of the problems. For another one, it's a problem originally by Dix, which I'm studying with Martin de Hoop and Matti Lassas. So imagine that we have point sources, which may be real or virtual, everywhere in the planet, and we can measure the arriving wave fronts then somewhere in a detector near the boundary of the surface. So the question is, does this then determine the reduced stiffness tensor A everywhere without any kind of assumption on the symmetries? So to geometrize, we'll consider a Finsler manifold, and we'll measure in some open subset U of this manifold. And in that set, we'll see spheres, and we'll know the orientations of those spheres, and we'll know the radii. So those spheres are wave fronts coming from earthquakes. So this is a geometric way to formalize that we at every instant of time we see where the wave fronts are. And that is our data. And the question is whether that data determines now the manifold. And what you can do is that you can follow this geodesics somehow backwards, so starting from your nodes at U, and then find the metric kind of along that geodesic backwards into your space. Okay, so again, I'm skipping a whole lot of detail here, but I just want to give flavors of the kinds of problems that I'm doing. And if you have some nice conditions, like fiber-wise analyticity, which just means that the Finsler metric is real analytic on every fiber, this information can be globalized, and it does not really determine the Finsler manifold, but it determines its universal cover. Well, that is not really an issue, because we know the topology of our whole planet. But from a mathematical point of view, there is this funny freedom to have covering spaces. Okay, so well, this fiber-wise analyticity is something that is actually valid in the elastic setting, so it is not a big deal. So this directionality of Finsler geometry, so things somehow depend on direction much more heavily than in Riemannian geometry. This is a major complication in comparison to the Riemannian version of the result from like 5 years ago. Okay, and for yet another example, there are distance functions with the same people and also the Saksala. And this is actually the example I had earlier in the talk. So I have a Finsler manifold with boundary, that is an isotropic elastic body with a surface, and every point in this manifold will determine the boundary distance function. So the distance is to all boundary points as a function of the boundary, and what we know is the set of distance functions on the boundary. So we don't know what the manifold is, we just see these travel times. And the question is, does this set determine the manifold M? And it turns out that in favorable situations it does, and unfavorable ones it does not. But there is always something that is invisible. So if you have a point on the tangents bundle where you somehow have a non-minimal geodesic, so there is a straight curve which is not actually the shortest one, then that will somehow lead to something we cannot see. Point is, we can fully describe what is a good set of a tangent bundle, and we can uniquely find the unknown beasts there, but we cannot find it elsewhere. So there is kind of a sharp result that we can see the thing here, but not elsewhere. And in Riemannian geometry, there are no complications of this nature. So this Finsler geometry, again, brings its own flavors into the game. So, but if you make additional assumptions that F is real analytic on every fiber, which is true in Riemannian manifolds and elastic manifolds, then this F is determined uniquely. So this is kind of the modeling thing that I mentioned earlier, that if you model at a correct level of generality, then you actually have much more strong and applicable theorems. For another one, which is scattering with the same folks. So what I had previously, I only had arrival times, but maybe I can also measure the directions of the waves coming in or out. So what this would mean is that for any two vectors on the boundary of the manifold, and those vectors pointing inward from the boundary, we would know whether the two rays starting from them meet, and if they do, we would know the total travel time. So this is just a mathematical way or the geometrical way to formulate a situation where we know single scattering measurements. So if you do single scattering measurements, this is what you would see from a geometrical point of view. And this we call the broken scattering relation. And it can see much more of the tangent bundle, so it can see much more of the manifold and the geometry, but there is still something invisible, and that is the so-called trapped set. Yeah, but global uniqueness can be done if you add assumptions. So if you assume it's reversibility and there is a foliation condition. Reversibility is valid on all these elastic models, and foliation condition is something that is actually measured to be valid on the Earth, which is kind of exciting. But it turns out, it seems that the foliation condition is not satisfied on the planet Mars. So this condition is actually a little subtle. But it's kind of a fortunate thing that we live on a planet which satisfies the nice geometrical conditions that we like, and it helps us prove our theorems. And in the Riemannian setting, you need very few assumptions, and that is usually the case. So when you have a broader model, you need to kind of make more strict assumptions on something else in order to cope with the difficulties that arise. Okay, and then finally a thing which is in a more kind of geometric nature called ray tracing. So you can follow seismic rays and you can study their variation, so study nearby seismic rays. And there are different coordinates you could use. So there are Cartesian coordinates, within are easy to define, but the equations are rather horrible. Or there are so-called ray-centered coordinates, which are more complicated to use, but they give more structure. And if you go even further, take this geometric picture and use the Fermi coordinates that come there and replace the coordinate derivatives with so-called covariant derivatives, then there's a lot of work to set it up, but once you do it, the equations are clean. And I want to give an explicit example. So, so you're looking at kind of two neighboring seismic rays, or these geodesics of phonons. There is a variation in position, which I'm calling Q, and a variation in momentum, which I'm calling P, and they will satisfy an equation like this, where these W's and U's and V's are some matrices. Okay, so that is what it looks like. But now if you replace this Q with the Jacobi field, which is the same thing, and you replace the momentum with the covariant derivative of the Jacobi field, again, the same thing. So it describes the exact same situation, but now the equation looks a lot more simple. So the W matrix goes to 0, the V matrix becomes the identity, and the U matrix becomes the curvature operator. So the beasts are much more geometric, but there is much more structure, and that makes analysis so much more tractable. Okay, and of course there is a lot more. I'll just mention quickly in words. So you can study spectral problems, you can listen to the planet and figure out whether the frequencies you hear actually tell you about the geometry. You can do geomath on Mars or other planets or moons. You can see the slowness surface as an algebraic surface, which it is. You can study linearized problems. So many of the problems are non-linear, but then you can linearize them, turn them into something a little easier. And that usually leads to ray transforms of different kinds, often with little data. Well, once you have these manifolds, you also have this freedom of coordinates, and that is something to be understood better. You can study rough geometry, so the Earth is not actually smooth, it is far from it. And underlying a lot of universe problems, all of these, both past and future, is this modeling goal. I'd like to build a complete theory of elastic geometry, and I am certainly not done, but I'm well underway to building a more complete understanding of this all. Thank you.
Okay, thank you very much.